So have you ever found yourself watching this race in large language models? It's exciting, right? But also kind of dizzying sometimes. And you start wondering, how do we make them not just bigger, but like genuinely smarter? And really importantly, more efficient, especially when you think about tackling those huge, complex, real-world problems, the ones that need, well, deep thought.
Welcome back, listeners, to The Deep Dive, brought to you by Neural Intel. We're the show that, tries to cut through the noise. We distill the key stuff from cutting-edge research and hopefully deliver the important bits, the insights, directly to you. As always, we're going to dive deep into the technical details and the big implications of the technology we're looking at today. Our focus is always squarely on the engineering, the innovations, the breakthroughs that are really shaping where AI is heading. Today, we're dissecting a paper that's, well, genuinely fascinating. It introduces a model that's pushing boundaries in a really significant way. We're talking about MiniMax-M1.
It's being presented as the world's first open-weight, large-scale reasoning model that features something pretty special called lightning attention. Think of it as a big leap forward in efficiently scaling what they call test-time compute. That's the crucial bit where the model is actually, thinking, generating its response. Our mission for you today is really to give you a shortcut, help you understand the core technical ideas here, what they actually mean for the future of AI capabilities, and maybe why this model could be a bit of a game changer. Everything we're talking about comes straight from our CISPO paper, MiniMax-M1, scaling test-time compute efficiently with lightning attention. Okay, so let's unpack this. We're dealing with a model built specifically for complex, multi-step tasks, and it brings in some really clever solutions to these long-standing technical hurdles in AI. From your perspective, what's the immediate headline? What really jumps out at you first?
Well, what's fascinating, I think, is that MiniMax-M1 isn't just another model that's, bigger, more parameters. It feels like a very strategic, almost fundamental response to these architectural limits that have always kind of plagued us when we try to scale up complex reasoning. It's really about doing more, thinking deeper, maybe more extensively, but with much, much less computational cost and that efficiency. It has huge implications for what these models can actually do in the real world, especially when we talk about sustained multi-step reasoning or, what we might just call thinking in an AI.
That's a great way to frame it. Moving beyond just bigger to smarter, more efficient thinking. Okay, let's start with the big picture. Scaling these reasoning models. We've seen large reasoning models, LRMs, right? Things like OpenAI's O1, DeepSeek R1. They've shown some remarkable success. And they've done it largely by pushing reasoning capabilities using large-scale reinforcement learning, RL. And the key idea they've really brought to the forefront, which MiniMax-M1 seems to amplify, is this new scaling dimension of test-time compute. So just to break that down, imagine an AI trying to solve a really complex puzzle. Older models with their limits, maybe they only get a fixed, short amount of thinking time before giving an answer. But what if you could give that AI more time, more resources, more compute effort measured in FOPs, floating point operations specific for the reasoning part while it's generating its response? The idea, which these LRMs have kind of proven out, is that the more computational power you give it during that thinking phase, the better it performs on really complex stuff.
It's a bit like giving a human expert, unlimited time and coffee to work through a tough problem instead of making them rush.
And that's exactly where we run into this fundamental wall with the traditional transformer architectures. If we step back and look at the bigger picture, it's really about tackling this, almost inherent curse of transformers when you push them hard, especially for deep thinking or super long inputs. The core problem is that ubiquitous softmax attention mechanism. It's powerful, yes, for shorter stuff, but it suffers from quadratic computational complexity.
Quadratic complexity.
Yeah, what that means practically. Say you have 1,000 words of input. If you double that to 2,000, the compute cost for attention doesn't just double, it quadruples. Go to 4,000 words, it jumps by 8 times, and it just keeps exploding like that. Quadratic scaling. It becomes a massive, often prohibitive bottleneck when you try to do extended, complex reasoning, because that naturally involves processing and generating really long sequences of tokens. Now, people have tried all sorts of clever things to get around this: sparse attention, linear attention variants, state space models, even linear RNNs, loads of ideas. But here's the kicker. Very few of these have really been proven out in large-scale, truly competitive LRMs. Almost all the top-tier reasoning models we see today, they still fundamentally rely on that traditional quadratically scaling attention. So it's not a minor hurdle. It's a deep, critical limitation that many have tried to crack, but arguably none have fully solved it in these big competitive models, until perhaps now.
And that's exactly the stage MiniMax-M1 walks onto, right?
The big goal was to build, and importantly open source, a large reasoning model that can efficiently scale that test time compute, directly tackling that quadratic barrier.
So the million-dollar question, how do they actually pull this off? The absolute core of it seems to be this hybrid architecture. It's a smart combination, a synergy of two big ideas, a mixture of experts, or MOE architecture, and that special lightning attention mechanism. Just to give a sense of the scale here, it's built on their existing MiniMax Text R01 model. It packs a massive 456 billion total parameters, which sounds enormous. But here's the clever part, the MOE part. Despite that huge total, only about 45.9 billion parameters are actually used per token. And these are spread across 32 different experts. So it means the model has this vast library of knowledge, but it's super efficient in how it picks what it needs for any given moment of calculation. That's like having, I don't know, a giant library, but knowing exactly which couple of books to grab for a specific question, rather than reading every single page.
Right, and that raises the question, why this specific mix? Why MOE and lightning attention? The mixture of experts part is brilliant for what we call parameter efficiency. Like you said, instead of firing up all 456 billion parameters for every single token, only a small relevant subset gets activated. This lets the model be incredibly large in its total capacity, its knowledge, its learned patterns, but remarkably efficient in the actual computation needed for each step. It's like having a team of specialist consultants, and only the right ones chip in on a particular problem. Saves time, saves energy.
Makes sense.
Then the lightning attention tackles that attention bottleneck we were just talking about head on. And this isn't just a minor tweak. It's described as an I/O-aware implementation of a linear attention variant.
I/O-aware, what does that mean practically?
It means it's designed from the ground up to minimize data movement, the constant shuffling of data between memory and the processing units. That's a huge hidden cost in standard attention. By being I/O aware and fundamentally linear, its computational scaling is linear with sequence length, not quadratic. Double the input length, you roughly double the work, not quadruple it or worse.
Okay, that's a fundamental shift.
It's a profound difference, yeah. That's where the real efficiency gain comes from for long sequences. And the architecture detail is key, too. They don't just swap out all the standard attention. It's a hybrid structure. They have a standard transformer block with softmax attention following every 7 transnormer blocks that use this lightning attention. This specific mix, this careful placement, seems crucial. It allows them to get that efficient scaling from lightning attention for most layers, while maybe still leveraging the expressive power of standard attention at certain points. It's a very deliberate engineered choice.
Okay, now this is where it gets really interesting for you, the listener. Think about what this means. Let's talk context length. MiniMax-M1 supports, natively, an absolutely astounding context length of 1 million tokens. Just put that in perspective. It's 8 times the context size of DeepSeek R1, which is a leading LRM itself. And it's genuinely an order of magnitude like 10 times greater than basically all other open-weight LRMs out there today. The paper table shows it clearly. DeepSeek R1 maxes out at 128K input tokens. MiniMax-M1, a full million. So think about the possibilities. You could feed an entire book, a novel, a dense technical manual, maybe a huge legal document into this model, or think about a massive code base, the whole repository for a complex software project, maybe hundreds of thousands of lines, or even, say, an entire year's worth of company reports, emails, internal docs, all of it. And the model can then reason across all that information, connect the dots, find patterns, spot inconsistencies, answer questions that need synthesis across that entire vast context. That's the kind of power this efficiency in handling massive context unlocks. It's a shift from analyzing snippets to comprehending whole domains.
And the computational savings, the FLOPs reduction you mentioned, is equally dramatic. It's really impressive. For instance, compared to DeepSeek R1, MiniMax-M1 uses less than half the FLOPs at a generation length of 64,000 tokens. And it gets even better. At 100,000 tokens generation length, it uses roughly 25%, just a quarter of the FLOPs.
A quarter? That's huge.
It's not just incremental. It's a fundamental change in efficiency. If you saw a graph of FLOPs versus sequence length, M1's line would be dramatically lower and flatter than traditional models. So practically, what does this mean? This huge efficiency boost helps in 2 key areas. First, inference, just running the model to get answers. It's much cheaper and faster, especially for long outputs. But maybe even more critically, it enables much more efficient and scalable reinforcement learning, RL, training. When you slash the FLOPs needed per token, especially at the super long sequence length, well, MiniMax-M1's design inherently makes RL training much more tractable.
Why is that so important for RL?
Because the rollout computation, basically generating the long sequences the model learns from and the latency involved, are often the biggest bottlenecks in RL training for these huge models. By making those steps cheaper and faster, they can explore more complex behaviors, longer reasoning chains during training, without the costs or time just spiraling out of control. Ultimately, this makes the model really well suited for complex real-world tasks, the kind that need you to process long inputs and generate really extended deep thinking. It kind of unlocks a new level of AI capability.
Okay, so we have this ingenious architecture. How do they actually, power it up? How do they train MiniMax-M1? The training journey sounds just as fascinating, especially because they use large-scale RL on this incredibly diverse set of problems, everything from pure math reasoning to messy, real-world software engineering. And that efficient architecture we just talked about, that was the foundation for making this intensive RL scaling even possible. It started with meticulous preparation. The first big step was this continuous pre-training phase. They took their base model, MiniMax-M1, and kept training it on an additional 7.5 trillion tokens. And this wasn't just random web data. It was, as they put it, a carefully curated reasoning-intensive corpus. They really obsessed over data quality, improving web and PDF parsing, enhancing cleaning rules, especially for math and code data, to make sure they captured relevant stuff. They specifically prioritized natural question-answer pairs and, importantly, avoided synthetic data at this stage. They even used semantic deduplication to keep the data diverse, not just seeing the same ideas rephrased. And the mix of data was strategic, too. They deliberately ramped up the proportion of STEM, code, books, and general reasoning data to about 70% of the total. This was clearly aimed at boosting its ability to handle complex tasks without hopefully hurting its general language skills too much. They even tweaked the training recipe itself, things like adjusting the MoE loss coefficient and adapting parallel training for bigger batch sizes to keep things stable during this massive run.
Yeah, that whole preparation phase is absolutely vital. It's like building a foundation for a skyscraper, right? You need it to be incredibly strong and stable before you start adding the complex upper floors. The focus on high-quality, reasoning-heavy data provides the rich raw material the model needs to learn complex thought patterns.
Right.
And then there's that long context extension strategy. That's a really critical technical point. They didn't just flip a switch and go to 1 million tokens. They did it in stages, 4 stages, gradually moving from 32K up to 1M. They found that just jumping straight up could cause, well, sudden gradient explosion. Think of it like the training, suddenly becoming unstable and breaking, especially with this hybrid lightning architecture. Apparently, different layers might learn or stabilize at different rates. So by doing this gradual, smoothed extension, they kept the training stable and effective, ensuring the model could actually use these massive context windows without falling apart. It builds that robust foundation needed for the intense RL phase.
Okay, so after that intense pre-training, soaking up all that knowledge, they moved to supervised fine-tuning, SFT. What was the goal there? Primarily, it was about instilling desired behaviors, especially things like reflection-based chain of thought, code-keat reasoning, using high-quality examples to guide it. This SFT stage is really important because it creates a much better, more stable starting point for the next phase, the RL phase, which could be trickier to manage. They made sure the SFT data covered diverse areas, but again, with a heavy focus on math and coding about 60%, really encouraging those long, step-by-step chain of thought answers. Now, let's get to the really novel RL part, the CISPO algorithm. This sounds like where they made a big leap in training efficiency. So what's the issue with standard RL algorithms like PPO or GRPO when you're training for deep, complex reasoning? Apparently, the way they handle token clipping can actually be harmful. Here's the idea. Imagine the model generating a thought process. It might produce some rare, low-probability tokens. But these tokens might be crucial for reflective behaviors. Things like, however, or let me recheck that, or wait a second, or even just, aha, These seem small, but they often mark critical turning points in reasoning self-correction, exploring a new angle. In standard RL, if these tokens are very unlikely, their important sampling weights can get really high. And traditional clipping just cuts these high values off to keep training stable. But the side effect is you're basically throwing away the learning signal from exactly those crucial rare tokens that represent insightful or reflective steps. If they get clipped, they don't contribute to updates, and the model never properly learns these complex reflective thought processes. And apparently, this was a particular problem for their hybrid architecture.
Yeah, that's a really subtle but super important point in RL. When a token is rare, its importance, sampling weight basically, how much impact its update should have, can shoot up. Standard clipping is there to prevent these extreme values from making the training go haywire. But the unintended consequence, exactly as you said, is you lose valuable feedback. You lose the signal from those vital, low-probability tokens that signify maybe a breakthrough or a crucial self-correction. It fundamentally limits the model's ability to learn nuanced, robust reasoning. It's a bit like teaching chess, but ignoring all the brilliant but rare moves because they're too unusual and might mess up the training stability.
Exactly. So their answer is CISPO, Clipped IS Weight Policy Optimization. And the core idea sounds elegantly simple, but really effective. Instead of clipping the token updates themselves, CISPO clips the important sampling weights. It's a key difference. Think of it like, instead of just deleting a really loud but important message because it's too noisy, CISPO just carefully turns down the volume of that message's importance score. It doesn't silence it, it just makes sure it doesn't dominate everything else unfairly. So what's the technical benefit? Well, this approach explicitly avoids dropping tokens, even those associated with large updates. But it still maintains enough entropy for stable exploration, so the model keeps trying new things, doesn't get stuck, and makes sure all tokens, even those critical low probability ones signaling reflection, actually contribute meaningfully to the learning process. When you look at the results, the paper has graphs showing that CISPO significantly beats other RL algorithms like ADAPO and GRPO on tough benchmarks like AIM 2024. They did a controlled test where CISPO got a 2x speedup over ADAPO.
Meaning it reached the same performance level using only half the training steps. So what's the takeaway here for you, the listener, whether you're a developer, researcher, or just following AI? It means they found a smarter, much more efficient way to train these models for really complex thinking. It's like finding a better workout plan that gets you to your fitness goals twice as fast because it uses every bit of feedback effectively. And this efficiency also drastically cuts the computational cost. The paper notes a full RL run for MiniMax-M1 took just 3 weeks on 512 H800 GPUs. That cost them about $534,700 in rental, which for training a model of this scale is actually a pretty significant achievement in making this kind of advanced AI more accessible.
And beyond CSPO, which is a great algorithmic innovation, they also hit these classic hidden technical challenges during the RL training, especially with the hybrid architecture. These often don't make the headlines but are crucial to solve. It's not just about the fancy algorithms, it's about getting the gritty, low-level numerical stability right. These things can absolutely make or break a multi-million-dollar training run.
Like what kind of things?
Well, one big one was a computational precision mismatch. They noticed this weird, problematic difference in token probabilities between training mode, when it's learning, and inference mode, when it's actually running. The correlation was only about 0.9x, which sounds close, but it was enough to stop the reward from increasing during RL. The model wasn't learning properly. They tracked it down to high-magnitude activations in the LM head. Basically, some numbers inside the final output layer were getting too big, causing precision errors.
Like rounding errors, but on a massive scale.
Sort of, yeah. Their fix was actually quite elegant. Just increase the numerical precision of that output layer to FP32, a higher precision format. That small change apparently realigned the probabilities, boosted the correlation to almost 0.99x, and fixed the reward issue. It's a perfect example of how a tiny numerical detail can have huge consequences.
Interesting. What else?
Another classic challenge, optimizer hyperparameter sensitivity. They used the standard AtomW optimizer, but the default settings just didn't work. The training wouldn't converge. The reason? The gradients, the learning signals were all over the place, ranging wildly from incredibly tiny 118 to relatively large 1E5, and weren't strongly correlated. Imagine trying to steer a ship when the rudder has totally unpredictable effects.
Bro, chaos.
Exactly. So they had to meticulously tune the hyperparameters, specifically beta 1, beta 2, and epsilon, to very specific values, B0.9, B0.95, and 1E15, to stabilize the whole process. Minor tweaks, major impact. And one more. Handling repetition. Sometimes, on complex prompts, the model would get stuck in a loop, generating pathologically long and repetitive responses. These weren't helpful for learning, and the large gradients they generated could actually destabilize the training. Simple string matching couldn't always catch these loops.
So how did they stop it?
They developed a clever heuristic based on token probabilities. If the model generated 3,000 consecutive tokens where each one had a probability above 0.99, they figured it was stuck repeating itself and just halted generation for that sample. This stopped the instability and actually improved training throughput. These kinds of granular engineering fixes, these war stories, really show a deep understanding of the model's guts and are absolutely essential for pushing the envelope.
That really does highlight the incredible amount of detailed engineering involved. Okay, let's shift gears slightly and talk about the data used for this intensive RL training. It wasn't just about how they trained, but what they trained on. They used a really diverse set of problems and environments. Crucially, scanning both tasks, where you could automatically verify the answer, rule-based verification, and more general tasks where feedback is maybe more subjective. Let's start with those reasoning tasks where they could get clear, rule-based feedback. What did that look like? For math, they gathered hundreds of thousands of high-quality competition-level problems. They put this data through a serious cleaning pipeline, removing incomplete problems, using embeddings to find and remove duplicates, strictly separating RL data from SFT data to avoid cheating, leaking answers. They even filtered out certain problem types like proofs or multiple subproblems and turned multiple choice questions into open-ended ones to force deeper reasoning. The reward. Based on getting the final answer right, verified by rules, plus a little nudge for good formatting. And importantly, they focused the RL training on problems in a specific difficulty sweet spot, about 50,000 samples where the model's initial success rate was between 0 and 0.9. Challenging, but not impossible. Then for logical reasoning, things like ciphers, Sudoku, they use 41 different task types. They use something called the SynLogic framework to synthesize lots of structured logical problems, complete with specific generators and rule-based checkers. Again, they carefully controlled the difficulty, making sure the problems were tough enough for strong models, but not completely out of reach for their base model. And the increased difficulties, the model got better. That gave them around 53,000 samples. For competitive programming, they started with public problems. But many lack good test cases, right? So they built an LLM-based workflow using their own MiniMax-M1 model to actually generate comprehensive test suites for these problems. Pretty meta. Then they filtered these based on quality and difficulty, ending up with about 30,000 coding samples. And maybe the most impressive part for verifiable tasks, real-world software engineering. They took inspiration from SWE Bench, using actual GitHub issues and pull request tasks like finding bugs, fixing code, generating tests. And to train on this, they built this sophisticated containerized sandbox environment. It wasn't just a simulation, it actually ran the code, ran tests, mimicked a real dev workflow. The reward was simple. Did the test pass or fail after the model's changes? This direct objective feedback led to several thousand high-quality SE training samples.
This whole diverse diet of data, especially these rule-based verifiable tasks, is just so crucial. Think of it as building that solid foundation in hard logic, in verifiable problem solving, where correct is unambiguous. The really clever technical aspect here is the systematic use of automated verification, whether it's a math checker, a logic engine, or that full code sandbox. That provides clear, reliable feedback to the RL agent, scaled up. It avoids relying solely on subjective human judgment for every single step. It grounds the model's reasoning in something objective, which hopefully makes it more reliable even when tackling fuzzier problems later on.
Right, which brings us to those fuzzier problems. Beyond the rule-based stuff, they also include a lot of general domain tasks. Here, rule-based checking doesn't always work, so they needed model-based feedback. How did they handle that? Well, for tasks that kind of had a ground truth, maybe STEM problems, factual questions where the answer is objective but can be phrased differently, they used a generative reward model, a GenROM. This GenROM acted like an AI judge, giving a reward on a 5-point scale based on accuracy and quality. But for tasks with no ground truth, like following instructions, creative writing, open-ended chats, they used prompts, sometimes with human reference answers. And here they used a pairwise comparison setup. Human reviewers looked at 2 model responses and just said which was better, or if they were equal, -1, 0, or 1. This helps tune for more subtle qualities.
Okay, but this leads directly to a really tricky technical problem. Bias in those reward models, especially the GenROMs, when dealing with long chain of thought reasoning. GenROMs often develop this subtle bias towards just longer outputs. They learn to prefer length, even if the quality isn't actually better.
Ah, the reward hacking problem.
Exactly. The model figures out, hey, if I just write more, I get more reward. And it starts adding fluff, becoming verbose without actually improving the substance of its reasoning.
Ugh.
They mentioned that their initial attempts to fix this offline, like tweaking the GenROM training data, just didn't work during the actual RL training. The model, being a clever optimizer, still found ways to exploit the length bias.
So how did they tackle it during RL?
This is pretty sophisticated. They implemented continuous online monitoring of length bias during RL training. So while the main model was training, they had a system constantly watching for signs of this bad length-seeking behavior. If it detected the model was just padding its answers to gain the reward, they'd trigger an immediate recalibration of the GenRM. It's like having a referee constantly watching for fouls during the game.
Real-time adjustments. Okay.
Yeah, and they also used RL side tricks, reward shaping, value clipping, normalization, basically trying to make the reward signal less sensitive to superficial things like length. The goal was to push the model towards optimizing for real substantive quality and correctness, not just verbosity. It shows a really deep understanding of managing these complex feedback loops in RL.
Okay, so they have all this diverse data, both rule-based and subjective, and they're fighting reward hacking. How do you blend all this together? How do you train one model to be good at both rigorous math code and open-ended general tasks? That sounds like a balancing act. Their solution was this smart curriculum approach. They didn't just mix everything together from the start. They began the RL training only with those reasoning-intensive tasks, the ones with the clear rule-based rewards. Build the foundation first. Then, gradually, they started mixing in the general domain tasks with the model-based feedback. What's the benefit of doing it that way? Well, it ensures that the model continues to refine its verifiable skills, solidifying that core reasoning ability, while progressively enhancing its performance on a diverse spectrum of general tasks. It helps the model learn to apply its reasoning skills appropriately depending on the context, and crucially, it helps prevent catastrophic forgetting, where learning new fuzzy stuff makes it forget the precise hard stuff it learned earlier. It's kind of like ensuring a student masters calculus before asking them to write poetry, but then hoping they bring some analytical rigor, even to their creative work. It aims for the best of both worlds.
That curriculum strategy is absolutely vital, especially at this scale, I think. Training stability is paramount. If you just throw everything at the model at once, especially with potentially conflicting or very different reward signals, it can easily become unstable or just learn poorly. By building that strong foundation in logical, rule-based reasoning first, they establish a solid cognitive base. Then, introducing the more subjective general tasks gradually allows the model to generalize and apply its reasoning more flexibly, hopefully without undermining those core skills. It's a really methodical way to build complex capabilities robustly.
Okay, so building on that successful RL training, they then push the limits even further, specifically extending the RL scaling to handle even longer thinking. Their initial RL phase had a 40,000 token output limit, which is already huge. But remember, MiniMax-M1's architecture with lightning attention scales almost linearly for much longer sequences. That was a key advantage. So they decided to leverage it. They pushed the maximum generation length during RL training up to an incredible 80,000 tokens. This is how they created the MiniMax-M1 80K model designed for truly marathon reasoning sessions. Now, to handle this massive jump in output length, they had to be really smart about the data they used for this extended training. They actually used the already trained 40K model to filter the data, removing problems it could already solve easily and focusing on harder math and coding challenges. And here's a really interesting, maybe counterintuitive point. They deliberately downsampled synthetic reasoning data for this phase. Why? Because they found that at these extreme lengths, the synthetic data tended to make the model's output repetitive and homogeneous, less diverse reasoning, and it actually destabilized the long context RL training. It really highlights how important diverse, maybe more natural or real-world data becomes for complex tasks at massive scale. And how do they manage the scaling itself, from 40K to 80K? They used a careful, staged window expansion RL strategy, not just one big jump. They went incrementally, 40K to 48K, then 56K, 64K, 72K, and finally 80K. And deciding when to move to the next stage wasn't just on a timer. It was based on empirical indicators. Things like perplexity converging, meaning the model wasn't confused by the new length anymore, and checking if the longest outputs were consistently hitting the current limit, suggesting the model was ready for more room. It was an adaptive, data-driven approach to ensure stability and good learning throughout this extreme scaling process.
Yeah, this is really where you hit the cutting edge, pushing these models into uncharted territory. And scaling up like this almost always reveals new, complex failure modes you didn't see at smaller scales. A big one they encountered was this pattern collapse problem.
Pattern collapse, what's that?
They noticed that, especially in the later stages of training within each new length window, like when training for 64K or 72K tokens, the latter parts of the generated sequences would sometimes just degrade, become incoherent or garbled text. And the perplexity, a measure of confusion, would shoot up for those later parts. Imagine getting a brilliant 50,000 token answer, but the last 30,000 are just nonsense.
That sounds frustrating. What caused it?
Their deep dive found that negative samples, the incorrect or bad responses, tended to get longer much faster than the positive good responses. This created an imbalance, leading to disproportionately large negative gradients, specifically targeting those later segments of the output. Basically, the model was getting hammered with negative feedback for the long wrong parts, which threw its learning off balance for those final tokens.
So how do they fix that?
They came up with a few targeted solutions. First, that early stopping for repetition we talked about helped prevent some pathologically long negative samples. Second, they adjusted the loss calculation, combining sample-level loss with token-level normalization, specifically to better handle that negative-positive sample imbalance. And third, they tweaked some RL hyperparameters again, decreasing the gradient clipping threshold and another value called epsilon xi to make the gradient updates more stable, especially for those problematic later tokens. These kinds of detailed, targeted fixes, born from really digging into why it was failing, show a deep understanding of the training dynamics at extreme scale. It's serious engineering.
Absolutely. Okay, so after all the architecture, the data, the training innovations, tackling these crazy scaling challenges, how does MiniMax-M1 actually perform? Let's get to the benchmarks. They ran it through a really comprehensive evaluation suite, covering basically everything: math, coding, software engineering, reasoning knowledge, long context using tools, agentic use, factuality, general assistance skills, the works. They use standard sampling settings, temperature 1.0, top P 0.95 for consistency. So what are the highlights? Across the board, MiniMax-M1 seems pretty strong. Mathematics performance is solid, comparing even against closed models like Seed Thinking V1.5. The 80K version hit 86.0% on AMI 2024, that second place among the open weight models they tested. For general coding, M1 80K mashed Qwen 3 235B on one benchmark, live code bench, and actually beat it on another full stack bench. So strong coding chops, reasoning, and knowledge. Highly competitive with the top open weight models, maybe just a smidge behind DeepSeek R1 on some tests. And for factuality and general assistant stuff, it beat many open models on simple QA and held its own against DeepSeek R1 and even Claude 4 Opus on the multi-challenge benchmark.
Yeah, those results across such a wide range really underscore the versatility and robustness they achieved. It's clearly not just good at one thing. It shows strong competitive performance across many fundamental AI tasks. And that breadth is crucial if you want a truly general-purpose reasoning model for diverse, real-world problems. It suggests that all that hard work on the architecture and training really did translate into broad capability gains, making it a serious player in the open weight space.
Okay, but this is maybe the real aha moment for you, the listener. Where does MiniMax-M1 truly stand out from the pack? It seems to be in the most complex, demanding scenarios. Let's talk software engineering again. Because they trained it using those execution-based sandbox environments, the M1 models, both 40K and 80K, schooled really well on SWE bench, verified 55.6% and 56.0%. That's significantly better than other open-weight models, showing a real ability to understand and fix actual code issues. They even mentioned using a unique two-stage process for finding the bugs, without relying on standard emitting retrieval, which kind of hints at strong pure reasoning. Now, long context understanding. This is where that lightning attention should really shine, right? And it does. Leveraging that massive 1 million token window, the M1 models significantly outperform all other open weight models on benchmarks like OpenAI, MRCR, and Longbench V2. Get this, they even surpass OpenAI O3 and Claude 4 Opus top-tier closed models on these long context tests. They rank second globally, only slightly behind Gemini 2.5 Pro. That's a massive win and a direct validation of the efficiency gains from the architecture.
Absolutely. That long context performance is a huge differentiator.
And there's more. Agentic tool used using external tools on TAU bench, the M140K model beat all other open weight models and even Gemini 2.5 Pro. That shows it can effectively interact with the outside world, not just reason internally. And consistently, across almost everything, MiniMax-M180K performed better than MiniMax-M140K. That's not just a number, it's strong empirical proof backing their core idea. Scaling test time compute really does lead to better performance. More thinking time equals better results. These specific areas, complex software engineering, reasoning over massive documents, intelligently using tools, these are where models often hit limits. M1's strength here really demonstrates the practical power of its innovations.
And there's visual evidence for the scaling benefit, too. The paper includes graphs plotting accuracy and generation length against the RL training steps. What these graphs clearly show is that the model isn't just producing longer answers over time, it's getting measurably smarter as it learns to think for longer. You see consistent, significant improvements in both performance metrics, like accuracy, and the average length of its responses during the RL training. For example, on tough benchmarks like AIM Math and live code bench coding, the average response lengths grew to exceed 20,000 tokens. That's extensive reasoning.
20,000 tokens on average, wow.
Yeah, and critically, the accuracy improved alongside it. AE 2024 accuracy saw substantial gains, climbing from around 68% up to 80% during RL. This strong correlation accuracy going up as response length goes up really hammers home the importance of extending that RL scaling. It confirms that enabling more extensive reasoning processes isn't just about being verbose. It directly translates into more effective, more correct problem solving. The length enables better thinking.
Okay, so let's try to wrap this all up. To recap this deep dive, MiniMax-M1. It's positioned as the world's first open-weight, large-scale reasoning model featuring that innovative lightning attention mechanism. This hybrid design is the key. It allows native support for inputs up to a massive 1 million tokens and generation up to 80,000 tokens, way beyond other open-weight models. This makes it uniquely suited for those complex real-world scenarios needing huge context and long multi-step reasoning. Beyond the architecture, they introduced the novel CISPO algorithm, a big deal for accelerating RL training and helping the model learn subtle reflective behaviors. And these combined innovations led to impressive training efficiency, that full RL run in just 3 weeks on 500 to 12 H800s. Its benchmark performance places it firmly among the best open-weight models available, right up there with leaders like DeepSeek R1 and Qwen3 235B. And it particularly excels in those really hard areas: complex software engineering, tool use, and especially demanding long context tasks. And maybe most importantly for the community, MiniMax-M1 is publicly available. GitHub, Hugging Face. Supported by standard frameworks like VLM and transformers, that open source release means huge accessibility. Researchers, developers everywhere can build on this, experiment, innovate. It could really accelerate progress.
Absolutely. And looking ahead, as we get better at scaling this test time compute to handle even more complex situations, efficient architectures like MiniMax-M1 have enormous potential. We can start thinking about tackling real-world challenges that are maybe still out of reach today. Things like automating complex company workflows, genuinely accelerating sophisticated scientific discovery, assisting in intricate design processes. These kinds of applications really need models that aren't just static Q&A bots. They need true AI agents, agents that can interact with environments, use tools, maybe control computers, even collaborate with other AIs. And that requires reasoning across dozens, maybe hundreds of terms of interaction, all while pulling in and integrating massive amounts of long context information. MiniMax-M1 feels like a really strong foundation for building those kinds of future agents. It makes that complex, multi-turn, long context reasoning seem not just possible, but computationally efficient, practical. So the provocative thought maybe is, what happens next? What new frontiers of problem complexity can AI tackle when thinking for longer isn't just feasible, but actually efficient and accessible?
That is a really powerful thought to end on. The idea of AI agents thinking longer, more efficiently, and the sheer scale of problems that might unlock. The implications are vast. For more deep dives into the latest AI and machine learning research, remember to check out our webpage. The link is in the bio. Thank you for joining us on this deep dive.